All right, this is take 2 on our video for number 38 on chapter 27. I hope this one goes better than the last one. Okay, so we're going to be looking at number 38 again in chapter 27. And if you don't have the book handy, no worries. We have the circuit diagram here in front of us. We also have our resistances labeled R1, 2, and 3, as well as our 2M EMFs. So what I'd like you to do right now is to take a moment and look at this symbol right here. That symbol is for the ground, and that literally means that it is the lowest potential, or 0 volts. You'll see that symbol occasionally, and that is literally the part of a circuit that is connected to the physical earth, the actual ground. What we really need to know is it's just 0 volts, and we see that it is connected to the 2 negative terminals on the 2 EMFs, and that makes sense, right? Because that's our lowest potential. All right, so what I'd like you to do now before we dive into the math is I want you to draw the directions of the currents through our 1, 2, and 3. So pause the video, take a moment, draw the currents. What do you think the current direction in our 1, 2, and 3 is going to be? And then we'll bring it back together in a moment. I've drawn mine in as shown here. We got I1 to the right, I2 to the left, and I2 to the right, I3 to the left, and I1 going down. I think those are pretty self-explanatory, giving the directions or the polarity of the EMF. However, if you find yourself on a problem in the homework that you're not sure which way the charge flow is going to move or what direction the current is going to go, don't worry, just assign it a direction. So literally on the diagram, draw the direction that you think the current is going. If you end up with that, let's say you identified it wrong, that's okay. What will end up happening is when you solve the problem, you'll get a negative value for your current. No worries, no big deal. You just know that you assigned it the wrong direction. What's so important, though, is that you assign each current a direction through each resistor, and you stick with that direction consistently throughout the whole problem. That's what's really important. Okay, so what I'm going to ask you to do is I'm going to ask you to use your junction rule, and I'm going to ask you to use your junction rule at point A in my circuit right there, and I'd like you to write your equation for your junction rule. If you don't know what a junction rule is, you need to go back to the previous video and learn about the junction rule, and then come back here. All right, take a moment for point A. I'd like you to use your junction rule. All right, so we have I1 is equal to I2 plus I3. All right, we've got current charge flow of 1 coming out. We've got 2 and 3 going into that junction. So therefore, we've got the I2 plus I3 is going to be equal to our current coming out, which is I1. All right, our next job is to use our loop rules. And I should back up for just a moment to make sure we kind of know where we're headed. Our goal, all right, so our overarching goal is to find I1, 2, and 3. That's our goal. So we want to find I1, I2, and I3. We want to not know its direction. Hopefully we got those right. And then also the size of those 3 currents. Okay, so then our next job is going to be to use our loop rule. And there are actually 3 different loops that we could use in this circuit. So one of the loops that we could use is the left-hand loop, which is this loop here. We could also use the right-hand loop. And then we could use the whole outer loop. Now, we don't need to actually do all 3 of those, and you can see that outer loop actually uses parts of the 2 inner loops, and then actually the 2 inner loops also overlap with the current through R1. So my suggestion would be to use 2 of those 3 loops. If you use the extra one, you'll just have an extra non-unique equation that is just kind of hanging out there like an appendix. You won't really need it. Okay. So what you're going to do, let's start with our left-hand loop. So we're going to try and start with this loop right here. We're going to go around that loop clockwise, and I'd like you to start at this point right there. So you're going to start at this corner right here, go around that loop clockwise, and I'd like you to write that loop rule. Again, if you don't know how to do a loop rule, go back to the previous video and learn how to do the loop rule, and then join us again. So take a moment and try that for just that left-hand loop. All right, writing that loop, starting here, and we go around our loop, and we have our EMF 1, and it's positive because we're going from the negative terminal to the positive terminal of the battery. And then we continue around our loop, we encounter a voltage drop around or across R2. We are traveling with the current, or we're transversing the loop with the current, so that's going to be a negative value. So we'll go negative, we'll call it V2. Again, we continue around our loop, our left-hand loop, and we're going, we encounter R1, and we're going with the current, so that voltage drop again is going to be negative, so we call that V1. And then we continue around the loop, just our wires, so we have no voltage drop or potential difference across there. So then our loop voltage adds up to 0, right? We end up at that same height. I would suggest rewriting that in terms of resistances and current. The reason why is we're not asked to find voltage drops at this point. We're just trying to find our currents, and so we need to write our equation in terms of the things that we're trying to find. Also, we have our resistance values, so it's helpful to rewrite those. So take a moment and rewrite that equation in terms of our resistance values. So, and you can actually put in your numbers for your EMF and know that our voltage drop across any of our resistors will be our current times our resistance. So we'll use that Ohm's law to rewrite. So this equation becomes an EMF of 6.0 volts minus our resistance for 2, which is going to be 200 times I2 minus 100 times I1 is equal to 0. All right, so the next thing that we want to do is we want to transverse the right-hand loop. So we're going to do that same thing, and we're going to go around the right-hand loop. Let's start at this point right here. I'm trying to get a different color so we can use that to help us separate our ideas. So we're going to have you start at this point right here, and we're going to transverse the loop again clockwise. So whenever you go around the loops within a problem, it is essential that you always are going around the loops in the same direction. So we're going to go again around clockwise. You're going to start at this point. Go ahead and take a moment and see if you can write an equation for the loop rule using the loop rule for that right-hand loop. So as we do that, you're going to notice that when we go over or across that I1, that we're going against our current. And so when we do that, we're actually going uphill. And so instead of having a negative sign in front of that, we're actually going to have a positive sign. So we're going to have a 100 times I1 plus a 300 times I2 minus 12 is equal to 0. Why are the signs that way? Again, I think you can see why I'm doing the voltages as they are. So we start here, our drop across R1 is going to be our current times our resistance, or R1 times I1. We're going against the current, so we're going uphill. So that means we're going to have a positive potential difference across that resistor. Again, we transverse the loop over to our R3 here. Same principle, our voltage drop is going to be our current I3 times our resistance I3. Or excuse me, our current times our resistance, 300 times did I write that wrong? This should be I3, shouldn't it? I'm glad that we caught that. That's I3. And again, it's positive because we're going against the current that we assigned, so we're going uphill. And then transversing the loop to our EMF source, we're going downhill on that one. We go from a high or a positive point to our negative terminal, which is going to be our 0. So we go downhill, which is why we have that negative sign in front of the 12. So our three equations that we're going to be using, so this is like an intermediary equation. I'm just going to kind of get rid of that. So the three equations that we're going to be using are shown here. We've got this I1, I2, and I1 is equal to I2 plus I3. Then we have our 6 minus 200 I2 minus 100 I1, and then our 100 I1 plus 300 I3 minus 12 is equal to 0. So now we have three unknowns. Those three unknowns are I1, I2, and I3. And we have three equations. So at this point, essentially, we have a system of equations. And when we have a system of equations, we can, and we have enough equations for each variable, right? So we have three unknowns and we have three variables. So therefore, we should be able to solve this. There's two different ways to go about solving this. One is through substitution, and that just takes some algebra. And the second way is to use matrices. I'm going to try to solve it for you both ways. I'm going to try to solve it for you as easily as I can, but it's going to be a little bit messy. So hang on tight, and I'll be back in just a moment to help you with that. My suggestion would be for you right now is to give that a shot. So you've got three unknowns. I would take a minute and I would start substituting in. See what you can eliminate, see what you can get rid of, and then try to get back and solve for, again, your I1, your I2, and I3. Where I'm going to start is I am going to start by substituting in each of my equations. I've got I1 here and here. So I'm going to take this and I'm going to actually substitute it in here and here. So my strategy is this. I want to try to start whittling down the number of equations that I have. And in doing that, it will help to whittle down those equations by reducing the number of variables. So I'm going to essentially substitute this right here, this I2 plus I3 in for my I1 in this equation and in this equation right here. So do that, start simplifying down, and then I'll be back in just a moment and we'll move on from there. Okay, so here's our simplified algebra. We're going to take our I2, I3, I2 plus I3 and plug it in for our I1s and simplify a little bit. And so that green one, I've substituted in I1 and I2 and then distributed that 100 across and then combined some like terms to end up with an equation that looks like this. So I have now, I have an equation that's just in terms of I2 and I3. And then at this point, my suggestion would be for you to solve that equation for one of those two variables. It doesn't matter which one. I'm going to ask you to solve it for I3. I don't know, I just picked it at random. It doesn't really matter. So then rearrange that equation for I3. So when you do that, you're going to end up with a function that looks like this. Now keep this one handy, maybe like somehow note that this one's going to be important for us because we're going to substitute that in a little bit to eliminate a variable. We're going to eliminate I3. Okay, so the next equation that we're going to attack is this blue one right here. And we are going to again substitute in for our I1. So we'll substitute in I2 and I3 for that. So we're going to leave this for just a moment. We're just going to kind of let it sit there for a second. All right, so then we're going to work that blue equation down. And that blue equation, we substituted in our I2 and I3. So for I1 here, we put in our I2 and I3. All right, so again, we have some terms that we can combine. So distribute the 100 across those parentheses and combine like terms to simplify it so it looks something like this. Now, at this point, I have an equation again in terms of I2 and I3. But just a moment ago, we solved our green equation for I3. So we're going to take that whole big equation and we're going to substitute it in right here for our I3. And in doing that, that is going to give us an equation just in terms of current 2 or I2. So we substitute that in. I keep thinking I need to scroll up when I really don't. So we substitute that in right there for I3, and you can see now that I have an equation. It's a little ugly, but not too bad, and it is simply in terms of I2, which is going to allow us then to solve for the current 2, right, or current 2. So at this point, just plug and chug, right, just algebra that whole thing out, and when you algebra that out, you're going to end up with a current. I just right, get rid of those 100s, distributed the 4 across the parentheses, combine like terms, all of those order of operations goodness, and we end up with a current that is 0.0109 amps. So once we have that value for I at 2, then what we need to do is we need to go back and substitute that into our other equation. So we take this value, our I2, which is 0.0109 amps, and we're going to substitute it back in up here in this equation that we highlighted just a moment ago to find I3. And when you work through and you find I3, you're going to find a value of 0.0273 amps. All right, 0.0273 amps. And that's a positive number. So again, we said that that's the right direction or the correct direction, which is good for us. And then, excuse me, we can go back and use our equation I1 is equal to I2 plus I3. And adding those two currents together, we will get a value of 0.0382 amps, which is great. We finished. Yay! The question also asks, I believe, for a potential at point A here. And the easiest way that I could tell you to do that, to get that potential at point A, we know our potential here is 0 volts, right? And we have a 6 volt potential here, or an increase in potential. You can find the potential difference across I1 by taking I2 times R2. So we got our I2 to be 0.0109, multiply that by our R2, which is 200, and we get 2.818 volts. And so then if we want to know our potential at this point, we would just take 6 minus 2.18, and you will get 3.82 volts. So the potential at point A is 3.28 volts. Again, I just took this number, right, because this is 0, I added this, and then I subtracted the potential difference across that point right there. Awesome. Good luck with these. I'll touch base with y'all later. Have a great night. Bye.